All right, hi everyone. I have tried making this video a bunch of times actually, and have not really been satisfied with the results, so I'm going to change things up a little bit here. There's essentially one major point I want to get across today and one calculation we're going to do. To set things up, I just want to basically review what we talked about last class briefly. So the setup is we have some data set, which we're thinking of being the data points x1 through xk. So these are some measurements you've taken or some values you've sampled, or essentially just something you've observed or measured, okay? Now we think of each of these values as coming from some fixed underlying distribution, probability distribution. So we think of these points as being sampled from that distribution. Now that distribution can be any kind of probability distribution, but for today's class, we're gonna assume that all of our data points are sampled from some underlying normal distribution with mean mu and standard deviation sigma. So we think of the values of mu and sigma as being the parameters of the model. Essentially, if we've restricted ourselves to thinking of normal distributions, then once you specify mu and sigma, you've entirely specified the underlying distribution. So we think of mu and sigma as being the values that parameterize the space of models that we're considering today. So what we want to do is we want to find the specific values of mu and sigma that make it so that maximize the probability, the conditional probability of obtaining the data x1 through xk, assuming the value parameters mu and sigma. So let me restate that slightly. Essentially what we want to do is we want to look at the probability that given the model M, or given the values of mu and sigma, what's the probability that the data set D that we observed actually came from the model that we're assuming is underlying the distribution. So assuming that we've found, or we're interested in some mu and some sigma, what's the likelihood that the data that we actually got came from this underlying model? Now, because this probability will be zero, because we're looking at continuous distributions, instead of trying to maximize this, because it's always zero, that doesn't make a lot of sense, what we're going to do is we're going to maximize the joint density function, the joint probability density function. So this function here, if we think of x1, x2, all the way up to xk as being random variables, then what this density function is doing is it's measuring it's giving us a probability density function of a joint probability density function of the variables x1 through xk, assuming we've fixed the values of mu and sigma. So this is a conditional probability density function, and for reasons that we saw last class, it actually becomes convenient if we actually maximize the logarithm of that function instead of maximizing the function itself. So we call this logarithm, we call it the log likelihood function. And if we maximize this log likelihood function, then essentially we're going to find the parameters mu and sigma that are sort of the most likely to have given rise to the data that we actually observed. Okay? So what we do is we take the derivative, to find the value of mu that maximizes this. We take the derivative with respect to mu, we set it equal to 0, and when we did that, we got this estimate here. If you look at it, what is this telling us? Well, it's just what you get when you take all of your data points, add them up, and then divide by the number of data points. So essentially, we're just taking the mean of the values we've observed. So we call that the sample mean, and we denote it by this x bar. And this is the maximum likelihood estimate. Maybe I should write it out in full. This is the maximum likelihood estimate for mu. Okay? Now, likewise, we can go through the same process and try to figure out what the maximum likelihood estimate is for sigma. In this case, we'll take the derivative with respect to sigma. We'll set that derivative equal to 0, and then we'll solve for sigma. This will be a homework problem that you work on. But the answer that you should get is this answer here. This is the maximum likelihood estimate for mu, or for, sorry, sigma squared actually, okay? So remember, sigma is the standard deviation, sigma squared is the variance. Now, there is something that's a little bit subtle going on here, and we'll talk more about this when we talk about the law of large numbers and the central limit theorem. But essentially, if we think of our data set as being a bunch of random variables, then our sample mean, which we can compute from our data set by just taking the average of all our points, that's also going to be a random variable. And this quantity here, our sample variance, is also going to be a random variable. Now, for reasons that we'll see later, it turns out that the sample mean sort of does its job really well. It's what we call an unbiased estimator of the true underlying mean. But the standard deviation actually is an underestimate. Typically, it underestimates the true value of the variance of the underlying distribution. So for that reason, typically what people use is, instead of dividing by the number of data points, instead of computing this piece here, so you compute the sample mean and then you subtract it from, you take every data point, subtract the sample mean, then square it, and then you add those all up and divide by k. That's what the maximum likelihood estimate tells you to do. Instead, we're going to divide by k minus 1, and we'll denote that by sigma hat. So this is no longer the maximum likelihood estimate for sigma squared, but we're going to call this the sample variance. So if that was a little confusing to you, that's fine. We will come back to this point later on. It's a subtle but important point. Suffice it to say that if you just solve this expression for sigma, you're going to get something that estimates the variance, but it underestimates it typically. So instead, we use this quantity here, which is a little bit different than the maximum likelihood estimate, but this ends up being an unbiased estimator as opposed to what the maximum likelihood estimate gives you. So let's put that aside for now. We will come back to that in a little bit. I want to sort of now set up what we're going to focus on today. And here's sort of a problem that we could focus on today. Suppose that we want to model the distribution of heights of students at BYU. So this is an example I brought up in class before. I think it's a really illustrative example. It's kind of simple, but I think it gets the point across. So we'll kind of stick with this and extend this a little bit. So suppose we go out and measure 5 students' heights, and we obtain their measurements in inches: 72, 76, 71, 75, and 73. So we have 5 measurements here of students with their heights. Now, if we assume that the underlying distribution of heights at BYU, if we assume that that distribution is a normal distribution with mean mu and standard deviation sigma, then we can actually find the maximum likelihood estimates for mu and sigma. And those maximum likelihood estimates, if we just kind of go back to what we just said, the maximum likelihood estimate for mu is going to be x bar, the sample mean. So in this case, it's 1 over 5 times the sum of the data points. So we have 5 data points, so we're adding up 5 of them. So it's going to be 1 over 5 times 72 plus 76 plus 71 plus 75 plus 73. We add all those up, and it should give us 73.4 inches. Okay. On the other hand, if we want to find the maximum likelihood estimate for our variance, that'll be the standard deviation is the square root of the variance. So we can do the square root of, well, let's do it in 2 steps here. That's going to be the square root of sigma squared bar, which is just the square root of 1 over 5 sum from I equals 1 to 5 of each of our data points, subtract off the sample mean. We've computed the sample mean to be 73.4 inches squared. Okay. And if we go ahead and compute that and plug our values in, if we go ahead and plug the different values for our x's in to here and sum those all up, we should get 4.3. Okay? Actually, I think 4.3 is, yeah. So you might say, well, hey, why did you use 1 over 5 when over here you said you should do 1 over k minus 1? I guess in this question I asked for the maximum likelihood estimate, and so that's why I did 1 over 5. But you really, I mean, in general, we'll actually be more interested in this quantity here, this sample variance quantity. So it doesn't, for this question, I guess I didn't, I said maximum likelihood estimate, so I probably should leave it as what I originally had. But in general, this is not really going to be the quantity we want. We actually want to find something else. Let's, you know what? I'm gonna leave this as the sample variance. So again, we will sort of make the distinction between these two quantities a little bit more clear later on. But for now, let's compute the actual sample variance because it's a better estimator. It's an unbiased estimator, and we get 4.3 here. Okay. So so that's great. That would then sort of tell us that, hey, the average height of a student, or rather, you could say that the heights of the students at BYU are normally distributed with a mean height of 73.4 inches and a standard deviation of 4.3. Now, if you think about that, though, that's a pretty tall height, okay? In fact, suppose that we knew that the actual height of adults in the US are normally distributed with a mean of 66 inches and a standard deviation of 3 inches, okay? So what we're saying here is there is some underlying distribution. If you look at sort of the height of all students, or sorry, of all adults in the US, there's some underlying distribution that looks like this, with mean mu pi at 66 inches. However, when we look at the points we sampled, they were all like 73, 76, 73. I think there was a 70 or something in there. I'd have to go back. Oh, they're right here on my left-hand side. So there's like a 71 here. So suffice it to say, they were all kind of clustered on the high end of this underlying distribution. So if we were to sort of just estimate, like we did on the previous page, we estimated the mean distribution for our BYU students, and the mu, or the estimate for our mu, was 73.4 inches. And so from our measurements, or the data we observed, our distribution would look something more like this. Okay? It would be normally distributed, but it would be shifted quite far from the underlying distribution of heights in the US. Now, there might be a few reasons for that. You might say to yourself, well, maybe BYU students are just generally taller than the average American adult. That might be true. I'm not sure if it is or not. But you might also ask, well, maybe our sampling was wrong. Maybe we made a mistake with sampling, and maybe we only pulled people from, we were standing outside the RB measuring the height of people after a intramural basketball tournament or something like that. So maybe the values in our sample were skewed, and they really aren't sort of representative of what we're trying to capture. So there's sort of a balancing act we need to play here, because it's possible that BYU students just are on average much taller than the average US adult male, US adult. But it's also possible that there were some problems in our methodology, some noise in our data, some errors and issues in the way that we constructed our experiment. So what we'd like to do is we'd like to somehow construct a model of the height of BYU students, but do it in a way that we take into account that we already know the underlying distribution of adults in the US. And we're claiming that their height is, 66 inches, 5'6". I don't know if that's accurate. I didn't look it up or anything. So since we know something about sort of the underlying probability, what this would tell us that it's actually quite unlikely, or at least should be unlikely, to get a mean that is sort of quite a bit higher than the national average height. So because we sort of have this prior information about what the height of an adult in the US should on average be, getting an average that's sort of so far above the national average should be kind of unlikely. And so somehow we want to factor that unlikeliness into our estimate to sort of account for the fact that there might be some error in how we sampled things. And so we kind of want to mix the two pieces of information. We want to take the information that comes from our sample and mix it with the information that came from our prior distribution. So how do we do this? Well, we're going to look at the maximum a posteriori estimate. So essentially the maximum a posteriori estimate is, you can compare it to like the maximum likelihood estimate that we just did. The difference with the maximum a posteriori estimate is now we're still trying to estimate this quantity here. We're saying we've got some data that we've observed, and we're looking to sort of find the model that maximizes this probability measure here. So we use Bayes' theorem to sort of rewrite this probability distribution, and then we can kind of ignore the probability of the data because the data is the data. We have the data in hand, and we're not looking at any other data sets, so that's sort of a fixed value. So the probability that we're looking to maximize is proportional to this probability here, okay? And so we've got sort of this probability that we're trying to maximize. We're trying to find the value of m that maximizes this. But again, all of these probabilities are actually equal to 0. So instead, what we maximize is we maximize their probability density functions. So this is the probability density function we want to maximize. But we know that it's going to be proportional to the product of these two probability density functions. Okay? So this little fish thing here, this alpha, means proportional to. So really by Bayes' theorem, there should be like the probability of the data down here, something like that. But because the data doesn't change, we're going to just drop that. And we can see that the thing that we want to maximize is proportional to the product of these two things here. Okay? So this thing here is the likelihood function. We spent some time maximizing that on Friday. On Friday, we just ignored the prior, and we just maximized the likelihood function. Today, though, we're going to actually maximize the product together, and we're going to see how these two pieces of information sort of play off each other. So once again, it's actually easier, instead of maximizing the functions themselves, it's actually much easier to maximize the logarithm of the functions. And so if you take the logarithm of both sides, the fact that they're proportional to each other means that there's just some scalar out front. We could call that scalar gamma or something. And when you take the logarithm of both sides, when you take a logarithm, you can split up products inside the logarithm. So when you take the logarithm of both sides, this splits up into a product, and whatever that multiplicative constant on front, it sort of contributes to some constant term on the end here, which we can kind of ignore because we're just trying to maximize it, so we really don't care what this constant value is. Okay? So this is the function we're trying to maximize. It's a logarithm of two probability density functions. And when it comes time to maximize, if we assume that everything is normally distributed, then we can just take each of these things and we can plug in sort of the PDF for the Gaussian right away. Okay? So we already saw on Friday what this thing looks like. It's going to be a product of a bunch of Gaussian, one-dimensional Gaussian distributions. Over here, for right now, we're going to assume that this is also normally distributed, okay? Meaning that the values of mu and sigma should satisfy some normal distribution, okay? And so what we do is we go ahead and we plug those in. So this is the exact normal distribution that we saw in class on Friday. It's just the product of a bunch of one-dimensional normal distributions. Whereas here, we're assuming that the mean of our distribution is normally distributed with standard so we're assuming that the mean of the underlying distribution is normally distributed, and that the mean of the possible mean values is this mu sigma, and the standard deviation is this sorry, this is mu pi and this is sigma pi. So just going back to our BYU height example, this is sort of the underlying the average height of the adults in the US, and this is the standard deviation. And so if we're trying to find the mean of this distribution here, the mean of our height of students at BYU, what we can do, we think of sort of the distribution that tells us the height of average adults. We think of that as giving us a probability distribution on the possibilities of the mu that we're looking for here. So in other words, if you were to sample a subset of students or a subset of people in the USA, you would expect that the sample mean that you find when you find their heights should sort of be normally distributed here, and the mean of all possible sample means that you find should be at this value here. So it's maybe a little bit weird when you first look at it, but essentially the mean of the distribution we're looking at is also a normally distributed random variable, and the mean of its underlying distribution is mu sub pi and sigma sub pi. Okay, so it's a little bit weird to think about, but mu itself, the mu that we're looking for over here is itself a random variable, and there's some constraints and information that we want to place on the distribution of that random variable. Okay, because it would be really unlikely to get a mean value that's way up here, and it would be really unlikely to get a mean value that's way up here. So we're sort of using this probability density function to capture the fact that we expect that the value of the mean that we find should be somewhere close to this mu sub pi. Okay, and that's exactly what this probability density function captures. So now what we're going to do is because this is a logarithm and we've got a product inside, we can split that up into a bunch of additive terms. So we get k times this term here, we get a sum right here. This term also splits off to give us a constant term here, and then we get this term here where the logarithms and the e's cancel. So things look a lot better. Now if we want to take the derivative of this thing with respect to mu, we can do that. When we take the derivative, these things don't depend on mu, so they go to 0. These things do depend on mu, and so when we take their derivative, we get this term here. That's what's left over. Now what we can do is we can multiply everything by sigma squared. So that gets rid of the sigma squared on the bottom, and we get just a sigma squared term up top here. And then what we can do is we can recognize each term in this sum has a minus mu. So we can actually pull that minus mu out, and then we can group it with the mu times this to get a term that only involves mu, and then some terms that involve everything else. Then since this is equal to 0, we can just bring this mu term over and then divide both sides by this piece here. And this is now the expression we get. Okay? So normally I would have stopped for questions there, but I guess there's no chance to ask questions. So there'll be time to ask questions on Wednesday's class. So we solve for this expression for mu, and we call this our x map, or this is our maximum a posteriori estimate for the mean x. Okay. Now it looks a lot like the sample mean. If we didn't have this term here, this would be exactly the sample mean. But what we're doing now is we're adding some extra pieces of information that somehow capture the prior probability distribution, or they capture information about the prior probability distribution. So let's see what this looks like in our example, and we'll kind of discuss it, for a second there. So going back to our BYU height example, the maximum a posteriori estimate for the mean height of a BYU student would be given by this expression here. So if we plug things in, our k is 5, all right? Our sigma squared, we don't actually know what the true value of sigma is, so what we do is we're gonna plug in an estimate for sigma, and the best estimate we have is that sample variance we computed. So the sample variance we found was 4.3. Oh, you know what? going back, I think I wrote down 4.3. Oh, this is supposed to be square root of 4.3. Sorry, I forgot to take the square root of this at the time. My apologies if that confused you. So we plug in the 4.3 there. We are assuming that, remember, in the setup to this example, we said that the standard deviation of our prior distribution is 3. So that's going to be 3 squared on the bottom, inverse. And then we're going to add up our points, our data points. And our data points are 72 plus 76 plus 71 plus 75 plus 73. Okay. And then again, we're going to get this term with a 4.3 on top, a 3 squared on the bottom, and then times the mu, pi, which was 66. So my laser pointer isn't working. Okay, which is 66. Okay. And whatever this value would be, I mean, I can compute it actually, but oh, sorry, this is 4.3. Is that 4.3? Just want to make sure I compute the 4. Yeah, so that's 4.3 square rooted. Okay, sorry, I just got a little confused there for a second. I didn't remember which value I had used. Yeah, okay, we're good. So, all right, so back to this example here. Okay, so what does this show us? If we compute this, and actually, let's do that. 4.3 divided by 9. Just plugging this into Mathematica as we go. 367 plus 4.3 divided by 9 times 66. Okay, so the height we get here should be okay, I may have made a little mistake here. Oh, yeah, so it's 72, sorry. So it's 72.7546. Okay, so notice the original mean value that we found, or the original estimate for our distribution's mean was 73.4 inches, and once we sort of factor in our prior distribution, we get 72.75 inches. So by including information about the prior distribution, we actually get a smaller estimate for the mean of our BYU height distribution. Now, if we look at sort of this expression here, notice I pointed out that this actually looks a lot like the sample mean that we were computing before, but it has these 2 extra terms in here. And the way that I think of this is that what this, this just looks like we're going to take an average here, but we get this extra term that sort of factors in information about the prior distribution. And on the top here, we get sigma squared, which is sort of, we're going to estimate that using our sample variance. And on the bottom, we have the variance of the underlying prior distribution. So the way that I think of this is like if my prior distribution, suppose it looks like this. Oops, what happened there? Suppose that my prior distribution is really sort of has a really small variance. So in other words, my prior distribution looks something like this. Okay? So this number is really, really small. Okay? Well, what that will do is it'll make this term here really, really big. And essentially, it's going to weight this mean value here much, much higher. Okay? So in other words, this mean value is going to contribute much more to the value it's going to be sort of weighted much more heavily. So this mean value here, this prior distribution mean, is going to sort of be much more important than the data that you observed. Okay? So if you assume that your prior distribution is really tightly clustered and you get a bunch of data points over here, well, because of how tightly clustered this distribution is, it should tell you that getting a mean way out here should be very unlikely. So it will sort of, because sigma pi is very small, it'll make this term really big, and this thing here will sort of be the main piece that contributes to our maximum a posteriori estimate. In other words, it should sort of pull our mean to be much closer to the mean of the prior distribution than sort of the mean of the data points. Okay. On the other hand, if our prior distribution is quite broad, like this, then this sigma down here is going to be quite large, in which case this term will be kind of smaller and become less important. And so if our prior distribution is quite broad and quite widely distributed, then essentially the mean of that prior distribution isn't going to play a big role in the maximum a posteriori estimate. And you're going to see that the mean of your sample points is going to sort of be the most important part when figuring out your maximum a posteriori estimate. So essentially, I think of this maximum a posteriori estimate as really just being some weighted average of the data points plus the prior mean that you found, and the terms that tell you how heavily that prior mean is weighted into this average are precisely sort of the ratio of the two variances. So if your data points are really widely varied and your prior distribution is really narrowly distributed, then you should expect this term here to sort of dominate and sort of play a really big role in the resulting estimate. On the other hand, if this is really small and this is really big, then you should expect that this term here is not going to play a very big role in the underlying estimate. So I'm going to stop there and post this video so you guys can watch it in time for class today. But save any questions you have. We can talk a little bit about this at the beginning of class on Monday and make sure everyone's squared away with it. So, in class on Wednesday. We'll see you then.